discussed excursions of Markov processes. So what we saw is that if we have, if the signal we're interested in is a Markov process with stationary transition probabilities, then the excursions are IID variables with values in some space of excursions. So then everything about this family of IID variables is summarized in the distribution of this IID family. And this is a distribution on the space of excursions. And then I gave you the description of excursions of a Markov process according to Ito. So Ito defined this excursion process, which is the collection of excursions from zero of a Markov process labeled by the value of the occupation time on each excursion. And then this is called the point process of excursions. And the main result of Ito's theory is that if you take any Markov process, which is recurrent at zero, so it goes through zero infinitely many times, so there are infinite collection of excursions, then if you look at the excursions of this process labeled by the occupation time, so basically labeled by the time they spend at zero, then this is in fact a Poisson point process. It's an infinite dimensional Poisson point process with values in the space of excursions. And this is a very interesting piece of information because a Poisson point process means that every time I take a set gamma of excursions and I want to count the number of excursions which fall in the set gamma, this is a Poisson process. But it's a Poisson process not in normal time, but in occupation time. So if I want to switch back to normal time, I have to use this inverse local time tau lambda. But this tells us a lot of things. It tells us that, first of all, I can count a number of excursions having a certain property. It will be a Poisson process in occupation time. I can switch back to normal time with the inverse local time. If I want to say what's the how much I have to wait for an excursion to have a certain property, then it's an exponential variable. And if I take two properties of excursions that define disjoint sets, then the number of excursions having this and that property are independent. So this gives us a lot of information to study the probabilistic properties of excursions. And then we saw that if we go back to our decomposition of the signal into delta excursions, now if the signal is Markov, this is an IID decomposition. This is a decomposition of the signal into IID concatenations. And so this is very useful because if I know the law of one of the elements in this sum, then I know the law of all of them. They're all the same law. And what is the law of one of them? Well, it's the law of the signal up to its at the end of its first delta excursion. So this shows that delta excursions are the right thing to look at because now I can decompose the signal into IID slices, each slice being having the law of delta excursion, and these delta excursions are independent and the same distribution. So this is great. So now it means that if I can get hold of the probabilistic properties of one delta excursion of this, or like the first delta excursion of my signal, then I can completely reconstruct the probabilistic properties of the entire signal, and all the things that I want to know about the trading strategy are captured by this distribution pi delta of the first delta excursion. Okay, so now, so what we want to see is how can we describe this distribution of delta excursions for different assumptions on the signal. And so for this, we need to describe the Ito measure, or the the distribution of excursions of the process. And as you saw, for what we're interested in, we're interested in the loss of the strategy, maximum loss, drawdown, things like that. These are related to the height, the amplitude of the excursion. because if you short the portfolio and then it continues to go up, then you lose money up to the maximum amplitude. So what you want to know is the distribution of this maximum amplitude M. And this corresponds to slicing the space of excursions into excursions with a given height M. And then conditional on the height M, you have a normalized excursion, if you want, vertically normalized excursion. It's an excursion which goes up to M and then comes back to 0. And this is different from, I mean, most of the things you have seen before, because if you fix the duration of the excursion, if you fix the duration to be equal to capital T, then in fact you have a bridge which goes from 0 to and hits 0 at capital T. That's a very different normalization, but the height is random. Here, if you normalize the height, then you have something which is much more complicated. But this has been studied for some processes like Brownian motion. I'm going to tell you what you get when you condition on the height. But this is what we want, really. What we want is conditioning on the amplitude, because we wanted the distribution of the amplitude definitely, because this determines the distribution of the loss. And then if we can describe what happens when you condition on the amplitude, well, that gives us a complete description of the process of the excursions. So I began to explain the one-dimensional diffusion case. So in this case, we know a lot about all these things. So if you have a one-dimensional diffusion described by the diffusion coefficient A, which is the square of the volatility, if you want, and the drift B, then you can introduce these two functions, the speed measure M and the scale function S, which are constructed in terms of an integral of B over A. And these two functions determine completely the properties of the process, including the properties of the heating times and the excursions. And so in particular, we saw that the heating time distributions for any level starting from any other level is given by ratios of these functions, which are called Wiener-Hopf factors, which are solutions of the eigenvalue problem associated with the operator G. Okay, so if you can solve this eigenvalue problem, then you can compute these phi functions, then you can plug them in here and compute. So this all depends on these functions M and S. Okay, so there are not many cases, unfortunately, where you can actually solve for these functions phi. The two cases really where you can solve them explicitly are Brownian motion and the Ornstein-Uhlenbeck process. I'm going to describe these two cases in more detail. But if you can solve them, and if you can solve this problem and compute the eigenfunctions of G, then then you have explicit expressions for the distributions, for the Laplace transforms of the distributions of the holding period, waiting period, trade cycle length, and then you have an equation for the number of transactions, or the number of delta excursions, which is which gives you again explicitly the Laplace transform of the expected number of delta excursions, which in this case is the expected number of trades in your strategy. So all the Laplace transforms can be computed in closed form if you have these functions, these eigenfunctions phi plus and phi minus. And also we can compute in closed form the maximum loss per trade cycle, the distribution of the maximum loss. So for this, we don't need the Wiener-Hopf factors. It's enough to know the scale function. And we can also compute the distribution of the realized profit. It's a binomial distribution whose expression involves, again, the scale function of the process. So if I know the scale function, we already have some interesting things. Scale function is not very difficult to calculate in many cases. And then if I can solve the eigenvalue problem, then I have the distributions of the the durations. So this lead to some explicit examples, which are widely used in pair trading, in fact. So the two examples which are explicit are Brownian motion and the Ornstein-Uhlenbeck process. So I'm gonna first spend a few minutes on Brownian motion. I already discussed some things yesterday, but very quickly. So the Brownian excursions have been studied in great detail in the literature, starting with Paul Levy and then followed by Ito, Chung, Williams, Pittman. There's a huge amount of literature on this. And there's some applications in finance related to Parisian options. So these are options involving the excursions or occupation time of the process. As I explained, for the applications we are interested in, we are interested more in the maximum amplitude of the excursions, because that's what determines the loss of the strategies we're interested in. So we want a description in terms of the amplitude. So this description was provided by David Williams. So sorry, Williams, not William. In the 90s, and his description is a very surprising one. So he gives a complete probabilistic description of Brownian excursions in the following way. First of all, the first result, which was known before Williams, is that, basically due to Paul Levy, is that the maximum height of a Brownian excursion has a power law density. So the density is basically 1 over m squared. Okay, so this is a description, and there is a normalizing factor. So so it means that, for our purposes, it means that if you're interested in the maximum height of the delta excursion, well, you already know that m is bigger than delta. So the density of your maximum amplitude, the amplitude of the delta excursion will be okay, indicator that m is bigger than delta divided by m squared, and then there's a normalizing factor, which is the integral to infinity. So we know the density, we know the distribution of the amplitude of a Brownian excursion, which exceeds delta. At infinity, it behaves like 1 over m squared times a constant. So it's a very heavy-tailed distribution, and it has infinite variance in particular. Then what the description of Williams, I mean, is a very sophisticated description. I'm not going to go into the details very much, but he says that once you fix the maximum height of the excursion, then the dynamics of the, so you have the maximum height of the excursion, then it's going to start from 0, reach this m, and then from m it's going to go back to 0. So so the result of Williams is that if you condition on the maximum height m, then the dynamics of the Brownian excursion before and after this maximum is described by 2 independent Bessel-III processes. So it's a very so a Bessel-III process, if you're not familiar with it, it's a diffusion with a certain drift and a diffusion coefficient, but so it has a drift. It has a drift, and so these are 2 independent Bessel-III processes. So it behaves like a Bessel-III process x1 from 0 until it reaches m. So it will be described by then the time at which you hit the maximum is described by the first hitting time of m of this Bessel-III process, and then it also behaves like an independent Bessel-III process from the maximum back to 0. So this is this gives you so the result of Williams is that if you pick 2 independent Bessel-III processes, you pick a variable m according to the correct density, which is the density of the maximum of a Brownian excursion, then you run x1 from 0 until it reaches m, you run x2 from that point until it reaches 0, then you paste these two pieces together, the resulting process has the same law as a Brownian excursion. A very intriguing result. And so it shows that this is a very rich statement. It says that we completely know how the Brownian excursion behaves. So, well, the distribution of the height is some heavy tail distribution, okay. But then from the first part of the excursion, when it's going up to reach the maximum, it's described by some Bessel process, some stochastic differential equation with a drift. And then the second part is also described by a Bessel process, but an independent one, and the two parts are independent. The two parts are independent. So this has many implications because it means that, you see, it mees that if I think of this as a signal which generates trading, so when you look at the excursion of your signal, you always try to forecast the signal a short time ahead. And you may think, well, if the signal is Brownian motion, it doesn't make sense to forecast. So there's nothing to forecast, right? Well, this result says, well, it is not completely nonsense to do a forecast, because in the first component, when I'm in the ascending phase of the excursion, actually, there is such a thing as a drift, but it's more subtle than the usual understanding of it, is that if I know that I'm going to reach a target M, then there is such a drift, and the drift is, in fact, the correct interpretation of the signal is the drift of this Bessel process. So again, I'm not going to go into this more in detail, but this description can be used to, get into much more detail than the results I'm going to show you, which will be only based on the distribution of the maximum M in the next few slides. So this is just show that in the Brownian case, we have a complete description of the dynamics of the excursions when we slice the space of excursions by the amplitude M. In each size M, we have a probability measure, which is completely explicit. It's the concatenation of the laws of two Bessel processes, basically, which are pasted together at M. So a very precise description by Williams. So what does that mean for the properties of the trading strategy based on a Brownian signal? Well, as I said yesterday, Brownian signal is a bit special because all these strategies are mean reversion strategies. They assume the signal has some mean reversion. Brownian motion, of course, has no mean reversion. But this is a very important case because it corresponds to the case where you think you have mean reversion, but in fact you don't. So you can think of this as a consideration of the impact of model risk on these mean reversion strategies. What happens to a mean reversion strategy when mean reversion disappears? Well, this is described in particular by the Brownian case. And as I explained briefly at the end of the talk yesterday, bad things happen. So bad things happen because in the Brownian case, when there's no drift, the duration between the trades, which correspond to the duration of these delta excursions, well, we already know their ID, but in the Brownian case, we know their distribution. It's a 1/2 stable distribution. So it's a very heavy tail distribution with infinite mean. So it means that you may have to wait a very long time for your trade to converge. And so this is always not a good thing for the trading strategy. So this is one problem. But there's another problem, which is even worse, and that's, I already alluded to it, the amplitude of the delta excursions has a heavy tailed distribution with the tail index 1. This is the density I alluded to here. Density is 1/m², so the distribution itself has behaves like 1/m at infinity. And the amplitude of the delta excursion corresponds to the maximum loss, because if you sell the asset at delta and then it goes in the other direction, it goes up and up, well, the maximum loss is the maximum height. So the distribution of the maximum height of the excursion is nothing else but the distribution of the maximum loss. And it will have a Pareto tail. And in the Brownian case, you can compute exactly this distribution. It's the probability of exceeding the loss m is delta over m plus delta. So in particular, as we saw, the maximum loss has infinite expectation. And if you put a stop loss m, so if you unwind the position and you reach the loss reaches capital M, then okay, the expectation is not infinite, but it's still it's going to be delta log 1 over m plus delta. If you integrate this from delta to m, you get this. So it means that it's going to go to infinity as n goes to infinity with a specific speed, which is a logarithmic. Okay. So it means that you can have an unbounded loss, and if you put a stop loss, you have this expression of the expected loss in M. So this has I think has very important implications, and I alluded to it at the end of the previous one, but I think it's very important, so I'm going to repeat this. It means that in this example, you have a strategy which is trading in one portfolio. This portfolio is assumed to be have a Gaussian dynamics, it's Brownian motion, so it cannot be simpler. So you expect your losses to be Gaussian because you have only one thing in your portfolio, and that thing has Gaussian increments. But it turns out it's not true. Your loss distribution is not Gaussian. It's a heavy tail distribution with infinite mean. Why? Well, because the intuition that if I know the distribution of the returns of losses of the underlying asset, I know the distribution of the portfolio. This is an intuition coming from static portfolios. It is not true for dynamic portfolios. And this example shows us that you can have a completely different nature for the distribution of the losses. Even the tail can change qualitatively when you go from static to dynamic strategies. So this means that this idea of using static approximations for risk calculations for dynamic strategies is completely wrong. It's qualitatively wrong, not just wrong, by another fact. It's qualitatively wrong because you can switch from a Gaussian distribution to a heavy tail distribution, even with infinity. So I think I like this example because it really shows that the usual approach of looking at the risk of a portfolio by looking at the portfolio today, rather than looking at the dynamics of the portfolio, can be completely wrong. Okay, so now we're going to look at a more commonly used example in mean reversion strategies, which is the Ornstein-Uhlenbeck process. So as I said, most of the papers on pairs trading or statistical or arbitrage strategies model the signal, the trading signals, as an Ornstein-Uhlenbeck process. So that's the most commonly used model because it has mean reversion and it's easy to estimate. Everything is known explicitly, Gaussian, easy to estimate, easy to simulate, and so on. So, it's luckily for this example, we also know a lot about the excursion, so we will have explicit results for everything we want. I'm going to spend some time on this. So this is the Ornstein-Uhlenbeck process. You can have a non-zero mean, but we can always center it when we define the signal to get a zero mean. So a zero mean Ornstein-Uhlenbeck process has this form. It solves a linear stochastic differential equation, and there are two parameters: the mean reversion speed alpha, and then the amplitude parameter gamma. So alpha is the speed of mean reversion. 1 over alpha will be the mean reversion time. And then this has a stationary solution whose variance is gamma squared over 2 alpha. And this is what you will estimate if you estimate the variance using a long time series of S. The solution is a Gaussian process with mean, well, the mean is, if a stationary mean is 0, but if you take initial condition, you have a non-zero mean. And the covariance is, well, this gamma squared over 2 alpha, and it decreases exponentially with rate alpha. In this case, the coefficients are simple. You have a constant, and here is linear. So the scale function is easy to compute. It's, I mean, it's not easy to compute. It's easy to write down. It's the primitive of this exponential of y squared times this constant, and the constant here is 1/2 of the stationary variance. Okay, so everything is known here. You can plug this in the eigenfunction equation that we saw earlier, and it turns out that you have an expression for the Wiener-Hopf factors phi plus and phi minus. This is all results dating back to Feller. So you have an explicit expression for the Wiener-Hopf factors, which are given here. I mean, there are integral expressions, but you can compute them numerically. And this leads to explicit formula, at least up to phi, at least something that you can numerically compute easily for the Laplace transform of the duration of delta excursions. And you have these forms here. So you have these functions phi plus and phi minus, and then you plug them in this formula. It gives you the Laplace transform of the durations of delta excursions. And okay, it's not clear from this formula at all, but using the properties of the Laplace transform, so the behavior of the Laplace transform at 0 determines the tail of the distribution. So from the properties of these functions, you can derive that the distribution of these durations decays exponentially. So unlike the Brownian case, it is not heavy-tailed, and this is due to the appearance of the mean reversion. There is a drift which pulls the signal back to 0, so it doesn't take an infinite. I mean, this makes the tail of the duration thin. Same thing for the holding period. So remember, the delta excursion is divided into 2, the holding period when it's going up from 0 to delta, and then the trading period where it goes back from delta to 0. So you can also calculate, so all of these are based on hitting times of 0 and delta. So the holding period can be also calculated, the distribution can be calculated. There are also independent variables with density given explicitly. And again, you can see that if you take t to infinity, you will have an exponential tail in t. It's with some constant that is not explicit. It depends on a lot of these things, but you have a exponential tail again. So all these hitting times have exponential tails. So also using the previous expressions and the fact that we have an explicit scale function for the Ornstein-Uhlenbeck process, we can calculate explicitly the tail of the loss distribution. So the probability that in each trading cycle, the loss exceeds a level m is given by this rate ratio of the scale functions at delta and m plus delta. So again, it's not totally explicit because S is given by this primitive of the Gaussian function, but Okay, again, this is easily computed by numerical. I'll show you the results in a few slides. And you can use this also to calculate the expected worst loss, again using the scale function. So here you have a benchmark model, at least. This is used as a benchmark to compare against other types of models. In this case, you have everything explicit. Okay, so all these expressions, distribution of the waiting time, holding period, the loss distribution, and others, they can be computed numerically, because the scale function is fairly easy to compute by numerically, and also these phi functions you can compute them with a single numerical quadrature. So this enables us to plot everything as a function of the parameters and understand what's going on in the trading strategies as a function of mean reversion, threshold level, standard deviation of the signal, and so on. So this is what I'm going to do, and we're going to look at this in some detail for the OU example, which again, if in the literature is the most important example. It's nearly the universal model. I mean, some people think that there's only one way to model a mean reverting signal. It's OU. That's so well so widely used. Okay, so what do we see? Well, so here are some plots using the formulas I showed you in the previous slides. So we're going to look at this mean reversion trading strategy. So the one-sided trading strategy, which corresponds to you wait until the signal reaches delta, you short the portfolio, and then you wait until the signal goes back to zero, and then you unwind the portfolio. And if that's without stop loss, and if there's a stop loss, well, when you short the portfolio, if it goes above delta plus M, then you unwind it there. You cannot keep it anymore. That's a stop loss strategy. So first, let's look at the case with no stop loss. So this is really, you follow the delta excursions exactly. So the first thing is the role of the mean reversion. Of course, this strategy only works if you have mean reversion. So if alpha is strictly positive, the case alpha equals 0 is the Brownian case, that we saw was very bad, in fact. And this is an important example because most of the risk management catastrophes, which you have been seeing in the last 30 years, are a strategy of this type. So I'm not, this is not just an academic example. So for example, you may have heard of the hedge fund LTCM, long-term capital management. This was a hedge fund whose partners included Robert Merton, Myron Scholes, well-known people. And this hedge fund blew up in 1998. They lost several billions of dollars. It was, and it was a very important event because they had transactions with many large U.S. banks. They threatened to destabilize the U.S. banking system, so the Federal Reserve had to intervene and so on. LTCM. It was a very traumatizing event in the financial market. So this hedge fund was doing mean reversion strategies of this type. So they were looking at pairs of bonds, 29-year versus 30-year bond, 15-year versus 10-year bond, and they were doing pairs trading on these bonds. And while there was mean reversion, the strategy worked very well. I mean, they were making a lot of money. But then in '98, something happened, and there was there was a crisis in Russia, and the spreads, instead of mean reverting to zero, they started going away from zero. So there was a very long excursion of the spread of the signal they were trading on away from zero. This excursion took several months, and that's when they blew up. So it was exactly a problem of this type. So this graph is really important graph. It shows that when mean reversion disappears, so you look at this expected maximum loss. We know that for the Brownian case where the drift is zero, it's infinite. Well, and this shows you as mean reversion becomes weaker and weaker. Well, this expected maximum loss is going to blow up, and it actually blows up like 1/alpha. Okay, so it's this is a very important graph, which shows you that if you're unsure about this alpha, if there's some uncertainty on the alpha, and typically this model is very simple. It assumes this constant mean reversion rate. If you have uncertainty on this, or if you think it's stochastic, it can range between this. Then you have a lot of uncertainty on the maximum loss, and if you want to do worst case risk management, this is probably the most important graph you need to look at. Okay, so this is often not something people look at because they assume there's mean reversion to begin with. Then you can look at, so what they look at is the graph B, this one, because they are worried about how to select the threshold delta. But this is a well-behaved graph because if you assume there is mean reversion, well, nothing very bad can happen. And basically, you're only worried about the optimal threshold, how to maximize your profit. So nothing very bad can happen here when alpha is fixed away from zero. So what you see is that, so this graph shows you for a given alpha, different colors correspond to different speeds of mean reversion. How should you choose your, how could you choose your threshold delta to, say, control the expected maximum loss? And you can see that there's always an optimal delta and so on. But I think the most important graph is the one on the left, which shows you how sensitive the strategy is to the mean reversion level of the signal. And so it means that first you need to make sure the signal is actually mean reverting. And if you want to use the OU model, you need to make sure it's mean reverting like OU model. Otherwise, this model can go very wrong. Okay, so now some more analysis based on our formulas about the influence of the threshold. So what we saw is that so these are simulations or explicit calculations using the formulas I showed you before in the OU model, no data here. So we saw that every time you trade in, every time you go in and out, you earn delta. So the realized profit after a certain number of trades is just delta times the number of trades. The number of trades up to time t is just the number of delta excursions d delta t. So delta d delta t is the expected, is the realized profit. So this is the expression of the expected realized profit in the Ornstein-Uhlenbeck model as a function of, again, the threshold delta. So here, here everything is expressed in terms of the stationary standard deviation sigma, because that's a natural way to think of a scale in this model. So one means one standard deviation of the signal. So, so in the applications, often you find in empirical papers that they choose delta close to sigma, but you can see from this graph that that doesn't seem to be optimal at all. I mean, it seems that the expected realized profit has a peak which is smaller than sigma. It's somewhere around half a standard deviation in these two examples. And the peak position depends on the mean reversion, but not so much really. So this is, as I said, there's a different approach to this, which is based on optimal control. There's a book by Tim Lung and Xin Li. They formulate the choice of delta as an optimal control problem, optimal stopping problem. So, and they solve it in the Ornstein-Uhlenbeck case. That's the only case where you can solve it explicitly. And they also find that the optimal level using this approach is smaller than half a standard deviation. So this is consistent with the explicit formulas you get here. But so it is not consistent with practice of using one standard deviation. Okay, so this is expected maximum profit, but now then you have the expected worst loss, which is a measure of the risk. You have the expected maximum expected realized profit, which is the measure of the income of the strategy. So you can now combine these two in an efficient frontier, which is shown in the graph B here. So this efficient frontier tells you the relation between the expected maximum loss on the horizontal axis and the realized profit for various parameters of your strategy. So what are these graphs? So this is, if you've seen the efficient frontier for mean variance portfolios, this is a similar idea. You have risk on the horizontal axis, return on the vertical axis. So if you go towards the north east corner, this is maximum risk, maximum profit. And if you go, so you would like to be high on the vertical axis, you make a lot of profit, but you would like to be low on the horizontal axis. You would like to have low risk. Of course, that's not possible because you have, if you increase your profit, the potential to increase the risk. But this efficient frontier tells you what's the optimal level of profit you can achieve for a given level of risk. So we can't do better than this frontier. So if you're above this graph, it means that you're suboptimal. If you're above this graph, it means it's impossible. You cannot achieve that. If you're below the graph, it means you're suboptimal. You can increase your profit by changing the strategy without increasing the risk at the same level of risk. So the efficient frontier here is you move along the efficient frontier by changing the only parameter of the strategy, which is the threshold delta. So the different points with the same color correspond to different choices for the threshold delta. This is the decision, the single decision the investor makes. And the star corresponds to the choice delta equals one standard deviation. So this is often used in applications. And the different colors correspond to different assumptions on mean reversion. I mean, the mean reversion of the signal is what it is. You cannot change it. And so alpha equals 2 is higher speed of mean reversion. Alpha equals 1/2 is lower, and then alpha equals 0.1 is even lower speed of mean reversion. So the blue curve is low mean reversion. The green curve is high mean reversion. I mean, higher mean reversion, like 20 times higher. And but then once the signal has the mean reversion that it has, so you don't choose that. It's a property of your market signal. And then your choice is how to move along this curve of fixed color. So what you see is that, okay, well, obviously, if you have more mean reversion, you have more profitability for a given level of risk. That's not so surprising. So the green curve is much higher in the vertical scale, but the curves have this similar feature. If you increase delta, you move along this graph, and then you at some point you start decreasing. So there is an optimal delta, which is shown also on the graph on the left. And the optimal delta is not one standard deviation, it's lower. Okay, so it's true in the different cases. In this case, it seems to be very close to one standard deviation, but in the KK cases of high mean reversion, it's, one standard deviation is really too high. You lose a lot of the profitability, the potential here. So this is a very useful representation. The efficient frontier tells you exactly what's the trade-off between risk and profit from the point of view of the choice of your threshold. Okay, so that's a good decision aid tool for analyzing these strategies, and is entirely based on excursion properties. So you can think of, so the horizontal axis is really the expected amplitude of the excursion, and the vertical axis is the expected number of excursion times delta. So these are, you can read off this graph completely from the distribution of delta excursions of your signal. Nothing else is needed. And in fact, I don't need the detailed description of the delta excursions like Williams. I just need the distribution of the maximum height and the duration, because the duration will determine how many excursions I see in a given time, and the height will determine the loss. So I just need two things really. So that's a good, but I need to get these two things right. So the model needs to correctly represent the height and the duration of the excursions. The other details, how do I get from 0 to m and get to 0? I'm not going to use it here, although it can be used for other things, but at least I need to get the duration and the height distributions right. Otherwise, these graphs will be wrong. I mean, will be wrong compared to the data. Now, you can introduce on top of this, as we said, a stop loss. So stop loss means that I buy or sell when I reach delta or minus delta, but then I don't wait until I reach 0 to unwind. I may stop earlier when I reach a loss level m. In that case, I lose m. So I either make delta or lose m, depending on whether I hit the higher level delta plus m. So this stop loss is often, exists in real trading strategy. You're not allowed to just lose any amount of money and just say, wait until it goes back to 0. I will eventually make money. And in fact, it's a stop loss that killed LTCM and all these other hedge funds that had mean reversion strategies. They had a finite amount of cash, so the stop loss was determined by how much cash they had, and at some point they ran out of cash, and they had to close down the strategy. So the stop loss is the main risk management parameter in these strategies. And if you put a stop loss, obviously you bound your losses at m, but then you also lose out some of the upside potential. You will decrease the return, because you're not able to wait until the end of the excursion and get the profit delta. So you will decrease the realized profit per cycle when you introduce a stop loss. And so these graphs show a little bit the role of the stop loss. So on the left, you see the realized profit per cycle when you have a stop loss of 0.1. So the profit cannot be more than 0.1, because you stop the excursion when you reach 0.1. So you cannot make a profit more than 0.1. And then it shows that this depends on the mean reversion. Really, the speed of the mean reversion will determine how much profit you make. But now it's bounded. Unlike the previous graph, it was unbounded. Now it's bounded by 0.1. So you sacrifice some of the upside by diminishing the risk, and it changes the efficient frontier. So you see here the efficient frontier, where I'm now changing. Well, it's a different graph from the previous one. In the previous graph, I was changing delta to generate the points with the same color. So here, each color is a fixed threshold delta. Okay, so let's focus, for example, on the red one. The red one is delta equals 1 standard deviation. And then I vary the stop loss levels between 0.1 standard deviation and 4 standard deviations. So as I increase the stop loss, I'm willing to take more risk, and I increase the expected maximum loss accordingly. Okay, so this is in the case of the Ornstein-Uhlenbeck process. So again, you can calculate expressions for these curves. I'm not going to show them because they involve these exponential functions. They are integral expressions. They're not explicit, but you can. So these are not these are all based on by numerical calculations from an explicit formula. So in this case, everything is known semi-explicitly. So you can see that the main parameter here is the stop loss. When you change the stop loss, you can generate a wide range of expected maximum loss. The unit here is standard deviation, so it goes from 1% to 7%. So really, stop loss is the most important decision to make in these strategies. Okay, so maybe this is I don't know. Sorry, I didn't pay attention to time. So maybe this is a good time to stop before the break. And then after the break, I'm going to compare this model, the OU model, which is again very widely used in industry, with the properties of the data, with some data examples to see, well, how do these distributions and graphs compare with what we see in the data? How good is the OU model as an approximation for the signals? And so are we happy or not? Okay. We can completely calculate many quantities that we're interested in, their distributions. And what you see is that for the study of these trading strategies, it's really determined by two quantities. The duration of these delta excursions, which determine how frequently you will trade, because you trade once every delta excursion. And then also it determines the expected, the realized profit, because you make a fixed amount of profit per delta excursion. So many excursions means higher profit. And this is generated by mean reversion. And then you are interested in the amplitude of these delta excursions, because the amplitude determines the potential loss or the risk of the strategy. So the risk return diagrams, which lead to the efficient frontiers in these strategies, are really, you can think of them as a duration versus amplitude of these strategies. Okay, so if you know the properties of the duration and the amplitudes of these strategies, then you know the risk and the return of the of the delta excursions, then you know the risk and the returns of the strategies. Conversely, this means that if we're interested in studying the properties, profitability, and risk of these strategies, we need to have a model which correctly represents the duration and the amplitudes of the delta excursions. If the model is great for other purposes, but gives an incorrect representation of the duration and amplitudes of delta excursion, then it is useless for the analysis of these strategies. It gives you the wrong insight. So this is very important to keep in mind. And now we're going to see if this Ornstein-Uhlenbeck model, which is used almost universally in these applications, does give a correct representation of the excursion properties of the signals, because that's what it needs to do. The other things, the other properties are not so important. The height and duration of the delta excursion is what you should look at to see if the model is good or not. Okay, so here are the two examples I'm going to use. It's the examples I showed you in lecture 1. So we take a pair of stocks in the same sector or a pair of funds which are correlated, and we build a signal from them by regressing one on the other. So the regression is run every day, and we fix the coefficient of the regression during the day. So let me show you, it was in lecture 1. I can show you more explicitly what is done here, just to recall, so you know what you're looking at. So yeah, so so this is the construction. You take two assets, P1, P2, and they're assumed to have a strong relation because they're in the same sector. And then you do the regression. P1 is regressed on P2. P1 and P2 are non-stationary, but if they're co-integrated, there exists a stationary combination, which then gives the result of the regression. So the coefficient W is determined by the regression, and the residuals are the signal that gives how far you are from the how far are the components of the pair from each other. And so to construct the signal, we just center the residuals by some moving average mean. And so the signal is really the centered residual of the regression, and it's the value, and it can be interpreted as the value of a portfolio containing one share in P1 minus W shares in P2, so a short position in P2, and then some cash. Okay, and S mean reverse to 0. So that's what we're doing here. Okay, so now if you use P1 and P2 Coca and Pepsi, this is what you get. This is for one trading day, and you do the regression every day. And so you can see that it is mean reverting, but not very fast. So like in one trading day, this is time in seconds. This is one trading day, 8 hours. So you see that, well, you cross 0, I don't know, 1, 2, 3, and maybe 20 times during the day, but then you can have this long excursion away from 0. So this is a very long excursion in seconds. So you have like something like 10,000 seconds. So more than 2 hours, you're going the wrong way. And this is also a long excursion. From here to here, you take like 3 hours. So that's one example. And here's another example. This is for the exchange traded funds STS-SH. I explained in the lecture 1. So this is over 1 year, so it's not comparable to the previous graph, but you can see, okay, it's not. It's a good example because there's a lot of mean reversion going on. It keeps, going up and down across 0. So every time it crosses 0, so for example, if you put delta somewhere in the middle of this here, you're going to do a lot of trades. It's a good signal. This is what people like in pairs trading. But you can also have large excursions away from 0. You can go very, very high, and then you in these large, we have these large points here, very large excursions where you can have huge amplitudes. And I've cut off the graph here. You can go even lower than this. Okay, so we see that these are interesting examples to look at. So, so as I said, the common approach is you estimate Ornstein-Uhlenbeck or autoregressive order 1 model, which is the same thing, on these signals, and you estimate the parameters, so the mean, so where to center the signal, the mean reversion speed, and the scale parameter. So for example, for the Coca Pepsi pair, if you measure time in seconds, which is the case on all my graphs, you get alpha, you estimate an alpha, which is around 10 to the minus 3. This corresponds to a mean reversion time 1 over alpha, which is around 800 seconds. So 800 seconds means, let's say if it's 15 minutes or so. So this corresponds to about, 20 or more cycles per day. And the graph we saw is roughly corresponds to that. So it's not one every second, it's every 15 minutes you have one cycle. For the STS-SH signal, we find, it's not alpha minus, it's alpha equals 0.0662, which is much higher speed of mean reversion. So it's like 10 to the minus 2 instead of 10 to the minus 3. So this corresponds to a mean reversion time of 1 over alpha. It's around 16 seconds. So this is a much faster mean reversion. In fact, I think I have a graph here of that signal. So this is a signal for STS-SH. So this is 1 day. And you can see that, there's a lot more mean reversion here. You don't have just 20, you have something like more than 100 cycles during the day. Okay, so Okay, fine. And then, so the idea is that then maybe we can model the signal with the Ornstein-Uhlenbeck with these parameters. Is that a good model? Well, as we saw before the break, one of the properties of Ornstein-Uhlenbeck is that it has mean reversion with a time scale 1/alpha. So if Ornstein-Uhlenbeck has mean reversion speed alpha, then the typical mean reversion time is 1/alpha. And the covariance decays exponentially at rate alpha. So it's exponential minus alpha h. If you look at the autocorrelation function, there's one in front and it's exactly exponential minus alpha h. So it means if I plot the autocorrelation function in logarithmic scale, I have to have a straight line with slope minus alpha. Well, that's what we can do for this data to check if it's really a good idea. So this is log of the autocorrelation function, or if you want, log of the covariance function with normalized to 1 at 0. But and for OU model, it's a straight line because it decays exponentially. So the log decays linearly with slope minus alpha. And if you take alpha equals 0.05, you see that you have a decay, which is at scale 1/alpha, which in this case is 20. So after the 20, you decay exactly by -1 on the log scale. So you drop by a factor 1/e. And this is how you estimate, the alpha for the data. You want to match this this point here, the speed of decay in the beginning. But then you see that the two curves diverge. The OU, of course, decays exponentially. The autocorrelation decays exponentially, whereas for the data, it decays much more slowly. And that's why it's useful to look at it on a logarithmic plot, because you can see on a logarithmic plot that it's really not an exponential decay. It's not an exponential decay, and in fact, it is a power law decay, because you can see that on a logarithmic plot, it decays more or less like a log. So it's actually, if you put it in log, then you will see a straight line. So this is a polynomial or power law decay of the covariance, which is a signature of long-range dependence. So the OU model is maybe okay for the short-term behavior, certainly not for the long-term behavior. So what does that mean? And we will see it in other graphs I will show you. It means that the OU model will work well most of the time. It will tell you correctly the frequency of small excursions. That's what determines the lower end of this, the left side of this curve. But it will incorrectly predict the frequency of the large excursions. These large excursions correspond to going away from zero a very long distance, and these will lead to long duration of excursions, and that doesn't count. So that's where the two models diverge. So it may correctly predict the expected realized profit for the frequent excursions, but it will certainly not correctly predict the risk or the tail of the distribution, because that's determined by the long excursions. And we will see this in other ways in the next few graphs. Okay, so this was about the autocorrelation function, or the covariance structure of the signal versus the model. Now let's look at another quantity which is linked, because they all are determined by the amplitude and the duration of the excursions. So this is the distribution of the excursion amplitude, which is the same thing as the distribution of the maximum loss when we don't have a stop loss. So here you have again the distribution of the maximum loss simulated from the OU model. Sorry, this is dotted line. So in the OU model, so you fit the Ornstein-Uhlenbeck model. Then in the Ornstein-Uhlenbeck model, we actually can compute analytically the distribution of the maximum loss. So you saw that we have an explicit formula using the scale function. So this is the dotted green line here, using the parameter estimated from the time series. And this is this blue is the actual distribution of the excursion amplitudes in the data. So what we see is that, well, again, so to explain this plot, this is a rank frequency plot. So it's like flipping the distribution on the other direction. So this is one. So this is this is a log-log plot where you see the rank and the frequency. So this is like looking at one minus the cumulative distribution function. And what you see is that, well, on one end for the, so it's like a flipped probability distribution. So for small excursion amplitudes, the OU gives a correct description of the distribution. So these are like very frequent small excursions. But once you go to the tail, so these are the excursions which determine the tail of the distribution. So these are large excursions. So large excursions, the data diverges again from the OU model. The OU model is very tame. The small and the large excursions are not very different in amplitude. In the data, it seems like you have you can have small excursions and huge excursions, which are one order of magnitude greater than the one predicted by the Ornstein-Uhlenbeck model. And this is what we saw in the graph. I mean, these are the points here. As you can see, you have from time to time, you have these huge blasts, the signal blows up, and this cannot happen in an Ornstein-Uhlenbeck. Ornstein-Uhlenbeck will correspond to the cloud of points in the middle. This is perfectly reproducible in Ornstein-Uhlenbeck. You will have lots of oscillations, lots of excursions, but the excursions will always be of scale 2 or 3 standard deviations. They will never go beyond that because it's a Gaussian process. So it has a Gaussian distribution at all times. The probability of ending up at 5 standard deviations is completely negligible. Here you have like several excursions in the same week, which are very, very large, like something like 10 standard deviations here. Same here. So this is impossible in the OU model, and this is what contributes to this tail up here. Impossible to get in the OU model unless you really blow up the parameters. So you can see that the decay of the covariance is qualitatively not like the data, and the distribution of the excursion amplitude is also logarithmically different. I'm not saying they're slightly different. This is in log scale. So if they're so different in the log scale, then maybe you should be concerned. So it's qualitatively wrong. If it's different on a log scale, I would say it's qualitatively wrong. The orange dot shows a fit of the empirical data for the excursion amplitude distribution with the Pareto, with the power law distribution, a Pareto distribution. So for the OU, the distribution decays exponentially. For the, so it corresponds to a log in the double log scale. For data, it seems like it has a regular varying tail or a Pareto tail and the slope here of the orange line is 1. So it seems like it's a very heavy tail distribution of amplitudes, more similar to the Brownian case, in fact. So this is, in fact, what you get in the Brownian case where there is no drift. So it seems like the data is a complicated thing. You have some mean reversion when you're close to 0, And then when you go really away from zero, it seems like you turn off the mean reversion. So it's like a stochastic drift, which is very complicated, and it's not well captured by a constant linear drift as in the model. Now, this is the amplitude of delta excursions for the other data set, STS, SH. So we saw that this other data set had much stronger mean reversion. It mean reverts at much higher speed. So what does the excursion amplitude distribution look like? So here I plotted it in two different ways. First in semi-logarithmic scale. So in this scale, an exponential distribution will show up as a straight line. And then in double logarithmic scale, log-log, where the Pareto distribution will show up as a straight line. So on the left, you see that, so this is for the OU, the orange, and then the blue is the data. So this is the distribution of amplitudes. So what you see is that, well, as expected, the OU exhibits an exponential distribution, which is a straight line in semi-logarithmic. So the vertical axis is log scale, the horizontal axis is normal scale. So the OU has an exponential distribution of amplitudes, not surprising. The data seems to be exponential. It seems roughly to give you a straight line, but the tail, which is the part that interests us, seems to be a bit different. So there's something of a mess here, which you do not see very clearly. But then if you go to double logarithmic, then you see more clearly. If you do a log-log plot of the same thing, it's the same graph, but in a different plot, you see now that, there's something interesting going on, which is similar to the Coca-Cola Pepsi data. You see that for small, so this is again, it is a rank order plot. So it's 1 minus the probability distribution. The tail is on the left and the center of the distribution is on the right. So for small excursions, the Ornstein-Uhlenbeck and the data have a similar behavior. So the behavior of small excursions, so the amplitude of small excursions seems to be well described by the Ornstein-Uhlenbeck model fitted to the data. But there is a breaking point, and this breaking point can be precisely characterized. It's somewhere here. And beyond that point, for excursions larger than some threshold, then all of a sudden, the blue curve, which is the empirical data, diverges from the Ornstein-Uhlenbeck, from the distribution of excursions of the Ornstein-Uhlenbeck. And all of a sudden, you have clearly a different regime, which very nicely coincides with the Pareto distribution of exponent 1. So the exponent 1 is the same as in the Coca-Cola Pepsi Cola data. So these are two different data sets, nothing to do with each other. But you can say that, again, we have this transition from strong mean reversion, Ornstein-Uhlenbeck regime on the right, to a second regime, which corresponds to the Pareto distribution. Again, the Pareto distribution is the distribution of amplitudes for a Brownian motion. So it is no mean reversion. So it seems like you switch off the mean reversion when you go far enough. So it mean reverts until you reach some threshold. Then it stops mean reverting, and then you have a long excursion, more or less like a Brownian motion, until it comes back. So this is a funny behavior, and it could be captured, for example, with a regime switching model, simply with two drifts: a linear drift, which you switch to 0 when you go far away, and then you have a 0 drift until it comes back again. So this will clearly give you this switch, and this is it's striking. I mean, it's very clean switch from it's like the blue curve jumps from the orange curve to the green curve at some point, and this point is very localized here. It's not all over the place. It's really so this is a very interesting behavior, which we see also in this case. Okay. But I think it's even cleaner here because we have many more cycles in this data. It's much more mean reverting, so you clearly see the difference. So this graph is consistent with the fact that the autocorrelation doesn't behave like an OU. It suggests some kind of regime switching behavior where you have a high mean reversion regime and then you switch to no mean reversion or zero, very close to zero mean reversion. And then you can get this kind of switching behavior. So this means that, looking at the structure of the excursions is very instructive, because if I just estimate an OU, I get one parameter. It will never tell me what's wrong with it. But if I look at the distribution of excursion amplitudes, I see, well, there's something very different from the orange plot, which is the OU. Okay. This is another way to look at the same data, but yeah, it's just the same in log scale. I'm going to just skip this. So you can see that clearly this is the rank order plot for the same data for the This is now the duration of the delta excursion. So here I showed you the amplitudes, and now we're going to look at the durations. How long are the delta excursions for the data? Again, for the OU, we have explicit expressions for the distribution of the durations. We showed them earlier. We have the Laplace transforms explicitly, and then you do an inverse Laplace transform, you do get this orange curve. It looks very flat because I take the log, but it looks very flat because the duration of the delta excursions for the Ornstein-Uhlenbeck is very concentrated along around 1 over alpha. So Ornstein-Uhlenbeck is characterized by a cycle length, which is very concentrated along around 1 over alpha. The cycles will typically be of length 1 over alpha. There is a small variance around it, but it's very small. So on this logarithmic plot, it seems, I mean, the variance is of order 1. So it's crushed when you compare it to the blue curve. The blue curve, on the other hand, is the distribution of durations of delta excursions in the data. And the distribution of delta excursions in the data, the durations are very heavy-tailed. You can have many, many short excursions of a few seconds, of a second. So we saw that the typical excursion length in the data is 16 seconds. But then you can have excursions in the data which are of the order of a day, 20,000 seconds. So there are excursions which last 20,000 seconds, 15,000 seconds, 10,000 seconds, so on. So it means that it's a very heavy-tailed distribution, and there is nothing of that type in the Ornstein-Uhlenbeck model. The Ornstein-Uhlenbeck model, the largest excursion it can generate is something like, of order 100 or 500. That's very low probability. So it's down here. Impossible to get the Ornstein-Uhlenbeck with these parameters to generate an excursion, which takes a whole day. But that does exist in the data. And of course, these very long excursions are also the excursions which have a very high amplitude. They're linked. So the fact that these two curves diverge is linked to the fact that these two curves diverge, because the maximum height, very high, is coming from the same excursions which have a very long duration. So this graph shows you that the Ornstein-Uhlenbeck model may give a good description of the duration of small excursions, but certainly not for the tail. It gets the tail wrong, very wrong. And it tells you essentially that these long excursions are impossible. But these long excursions are the danger for this strategy. The risk of this strategy is exactly these very long excursions which go in the wrong direction. So it means you completely miss the risk of your strategy with this model. This was for the SDS-SH data, but we can do the same we did the same for the Cocoa Pepsi data. And here, exactly the same picture. So what is this? Again, this is more detail. I just, in the previous one, I plotted the distribution of the duration of the delta excursion, but as we saw, delta excursion is split into two. The time it takes to reach delta from zero, and then the time it takes to reach zero from delta, so the up and down phase. So we can look at each phase independently because in the OU model, they're independent variables and they have a explicit distribution for each. So here I split them into two parts, the waiting period and the holding period. And you see that, well, so the green dot is the distribution, again, in semi-logarithmic scale of the waiting period for the OU model estimated from the data. So this green dot is calculated analytically from the formulas we had, given the estimated parameters. And then the blue is the empirical distribution of the holding periods or waiting periods in the data for Cocoa Pepsi. And this is for delta equals sigma, one standard deviation threshold. So what we see again is that, for the waiting period, again, for both cases, for small excursion, so the center of the distribution, maybe it's roughly in line, but certainly when you go to long waiting periods, the tails are totally different. And especially for the holding period. So the waiting period, maybe you don't care about so much because the waiting period influences the trading frequency, but during the waiting period, you're not holding the stock, so you don't really care. But the holding period is what you really care about because that's when you can have a loss if it goes in the wrong direction. And that determines, this is where you're trading. And this is where they diverge a lot. So this is so the waiting period is the time you spend below delta. The holding period is the time you spend above delta. And that is where the data really doesn't look like the OU. So the OU, as you can see here, it goes up to 5,000 seconds, the longest excursion above delta is 5,000 seconds according to the OU model, at least with these probabilities, and we go down to 10 to the -4. So it tells you that with probability 1 over 10,000, with probability 1 minus 1 over 10,000, you will stay below 5,000 seconds. The excursion does not exceed 5,000 seconds. Whereas in the data, it actually can reach 20,000 seconds, which is 1 day. So it can stay above the level for the entire day. It means you will not trade during the entire day and you will have to unwind that loss. So this means that, again, the length of the duration of the delta excursions is qualitatively different in the distributions are qualitatively different in the OU model and in the data. So same, different data set, same conclusion, okay? So these graphs, really what they show is that the predictions, or I mean the assertions of the Ornstein-Uhlenbeck model for the height and duration distributions of the delta excursions are really not great. They're qualitatively wrong. They don't just give you the wrong level, they give you the wrong extrapolation, the wrong asymptotics. They're logarithmically on a different scale. There is a difference of a factor of 4 between this and this. It's quite bad. So this means that this Ornstein-Uhlenbeck model, before you jump into the Ornstein-Uhlenbeck model and start doing stochastic control and optimal stopping with it, you should really check if it's a good description. And the only thing we want here is for the model to give you a correct distribution for the amplitudes of the delta excursions and the correct distribution for the duration of the delta excursions. We don't want infinitesimal details to be correct, just these two global quantities, but they're not. So this means that this Ornstein-Uhlenbeck model is really probably not a good model for this application. And this application is, I mean, this is one example. All these strategies, as we showed you, are sensitive to the height and duration. If you don't get them right, well, probably not a good model. So it means that this Ornstein-Uhlenbeck model is not good. And what could be a better model? Well, what we see here, a hint that if anything, you need some kind of regime switching model where you could have possibly strong mean reversion with a linear drift near zero. But then if you go far away, then this should be disabled. And this leads to these long excursions away from zero, which give you a correct tail. So the tail of the tail looks like a Brownian excursion, whereas the center looks like an OU. So this is a kind of strange animal, but it is not very difficult to build a model which does that. And we will do that tomorrow. So tomorrow I will show two different approaches to build models for excursions. So we want to construct models that have the correct properties for the excursions of the process. And by correct, I mean give you a realistic distribution of amplitudes, give you a realistic distribution of durations, and if possible, a realistic joint distribution for these two. And we will see that there are two main approaches that we can use here. One is some kind of a regime switching model. And the regime switching really happens at some level. So it's also determined by some heating time of some level, as you can see here. This graph is very interesting because it shows you really switch at a specific level. So and that's nice because if we can incorporate the regime switching through some heating time, then everything is determined by heating times of excursion. So it really is determined purely by a collection of excursions. So that will lead us to construct Markovian models, which have the desirable properties for height and duration of excursions. And then a second approach I will describe is a non-parametric approach, which is not based on SDEs or Markov models, but based on data. And there we will not assume the Markov property, and we will be able to look at excursions of more complicated things like a fractional Ornstein-Uhlenbeck or something which even has unknown dynamics. And this non-parametric approach will be based on a data set, and we'll see how, if we have a data set which gives us enough information on the delta excursions, can we build a scenario generator, a simulation engine for paths, which will give paths with the correct behavior of delta excursion. So that will be the non-parametric approach. So I will describe these two approaches tomorrow, and then we will compare back to this data to see how good they are at fixing the problems that the Ornstein-Uhlenbeck model seems to have in these examples. So maybe I stop here and take some questions if you have.
Okay, time for questions in the chat. No questions, no comments.
Okay.
No questions. Okay, so we continue tomorrow.
Thank you. Thanks to Vanessa, so she can post them.
Thank you very much for all, and we see tomorrow.
Thank you very much.
Okay. Thank you.